Math 2414, section 9.2, calculus with parametric curves. Video 6 of 9, example 3. Find the area under one arch of a cycloid. Surprise, it's the cycloid again. Just a reminder that the parametric equations of the cycloid are the x-coordinate as a function of theta is r times the quantity theta minus sine theta. The y-coordinate in terms of theta is r times the quantity 1 minus cosine theta. Also, we've already discovered that it takes one cycle, one period of sine or cosine to complete one arch of the cycloid. So we're going to be integrating in terms of x-coordinates from 0 to 2 pi. But when we set up the integral in parametric form, we don't integrate over the x-coordinates, we integrate over the value of the parameter. So we need to make sure we know what theta equals at 0 and what theta equals at 2 pi. It won't surprise you, it's going to equal 0 and 2 pi. All right, in fact, we can take that for granted. Again, even though this says 0 to 2 pi on the x-axis, the theta is the angle that we're rotating, and this function tells you where you are x-wise. Yeah, we're going to have, 0 to 2 pi. I'm making a mountain out of a molehill here. All right, so let's think about the values of theta. At the beginning, theta is equal to 0 because we haven't rotated any. And at the end of this arch, theta is equal to 2 pi. Again, don't read too much into the theta matching those x-coordinates. That is just at the, that is just at 0 and 2 pi. All right, so if we start at 0 here, we're moving from left to right. But we should confirm that our first derivative of the x-coordinate is greater than 0, because that's when we get to integrate from left to right. So let's start by examining dx d theta, as if we didn't know what this graph looked like already. The derivative of x with respect to theta is r times, because it's constant, derivative of theta is 1, derivative of negative sine is negative cosine. Can you convince me that this is never negative? And I think I need to backtrack briefly that in fact, I can fix what I need to fix here by simply making both of these say greater than or equal to, less than or equal to. It's okay if your derivative is 0 as long as it never becomes negative. That's when it would go backwards. Or if it were negative, it's okay if it's 0 as long as it's not positive, because that's when it would reverse and go to the right again. So as long as our derivative doesn't change signs, I should say, doesn't switch from positive to negative or vice versa. Our derivative of this, but there's a pretty convincing argument that this will never be negative. Cosine theta is always less than or equal to 1. In fact, it's trapped between negative 1 and 1. You should all know that. So how can I convince myself that the derivative of x with respect to theta is always non-negative? Well, simply by taking this inequality and building it up into the derivative. To do that, the first thing we'd have to do is put a negative on it, which means we'd have to multiply everything by negative 1. Now be careful, we're about to multiply inequalities with by a negative. That's going to reverse the signs. 1 is greater than or equal to negative cosine theta, which is greater than or equal to negative 1. At that point, we can flip it around. Just read it from right to left. Negative 1 is less than or equal to cosine theta, negative cosine theta, which is less than or equal to 1. So this is equivalent to saying what I just said. Negative 1 is less than or equal to negative cosine theta, which is less than or equal to 1. And now to build it up to this derivative, I add 1 to all three parts of this compound inequality. Add 1 here, we get 0. Add 1 here, we get 1 minus cosine theta. Add 1 here, we get 2. Multiply everything by r, which we're assuming is positive because it's a radius. And we get that our derivative is trapped between 0 and 2r, our x derivative. And more importantly, it's not going to get negative. Now, you could have looked at this and said, well, the largest cosine can get is 1, so the smallest the subtraction problem can get is 0, and that would be okay. But we can algebraically verify that the derivative is always going to be greater than or equal to 0. And since we can verify that, and we just did, at this point we can say the derivative is always greater than or equal to 0. And again, the reason that's important is because we can't calculate the area under a parametric curve if it changes directions x-wise, because otherwise the curve retraces itself and we start overlapping areas. All right, so we're doing this. Our derivative is greater than or equal to 0. Therefore, the area is simply going to be the integral from the leftmost value of theta, so 0, to the rightmost value of theta, 2 pi, of the y function, which is r times 1 minus cosine theta, times the derivative of the x function, which we already found here, r times 1 minus cosine theta. Huh. I don't know why I didn't observe that before, but the derivative of the x is the y, d theta. The r's being constant factors can be pulled out, so we have r squared integral 0 to cosine, 0 to 2 pi. And then the 1 minus cosine theta is just screaming to get squared. So if we FOIL it out, we get 1 minus 2 cosine theta plus cosine squared theta. Oh goody, we're integrating a squared trig function. That means we have to go get our power reducing identity. We haven't seen it in a while, but remember that cosine squared theta is equal to 1/2 plus 1/2 cosine of 2 theta. So that gives us r squared times the integral from 0 to 2 pi of 1 minus 2 cosine theta plus, replace cosine squared theta with 1/2 plus 1/2 cosine 2 theta, d theta. The 1 and the 1/2 should get combined to make a 3/2. So we have the r squared integral 0 to 2 pi, 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta d theta. And now we can integrate. We had to get rid of the power in the trig function, in this case by using the power reducing formula. And as much as I don't want to erase this, I don't want to erase that even more. So we'll just continue that problem over here. It is time to take the antiderivative with respect to theta. Antiderivative of 3/2 is 3/2 theta. The antiderivative of minus 2 cosine theta is minus 2 sine theta. And if you have to go slower with your trig antiderivative, so be it. The derivative of 1/2 cosine 2 theta technically would use a u sub, u equal to 2 theta. So du would equal 2 d theta, u is equal to 2 theta, du equals 2 d theta. There's currently no 2 part in front of this, so in order to balance the du package, I would have to multiply by the reciprocal of 2. In other words, I'd have to pick up another 1/2 along with this one. Well, 1/2 times 1/2 is 1/4. So the antiderivative of 1/2 cosine 2 theta is 1/4 sine of 2 theta. And this is all evaluated from 0 to 2 pi. Now let me show you a dirty trick that I shared with my Calculus 3 class, because we run into this situation quite a bit. Sine of theta has a period of 2 pi. Every 2 pi it repeats. That means any two values that differ by 2 pi are going to come up the same. When I evaluate this part of the antiderivative at 2 pi and then evaluate it at 0, I get the same results, and they're going to be subtracted, meaning that this portion will disappear when I evaluate it at the limits of integration and subtract. For sine of 2 pi, when you double the angle, you cut the period in half. You're going twice as fast, so it only takes half as long to make a complete revolution around the unit circle. The period of this is not 2 pi, but pi. Any two values that differ by a multiple of pi are going to come out the same. Okay, 0 pi, I'm at the same place. 2 pi, I'm at the same place again. So using the same argument, because the difference of these two is a multiple of the period of this, when I evaluate this part of the antiderivative at 2 pi and 0, they will come out to be the same values. So when I subtract the antiderivative evaluated at 2 pi minus the antiderivative evaluated at 0, these parts will cancel each other. So this part evaluates to be 0 when you subtract what this is equal to at the limits of integration. This zeroes out, the only thing left is this. Now, if that made sense, great. If it didn't, then don't do it. If it didn't make sense, put the 2 pi everywhere, work it out. Put the 0 everywhere, work it out, and you'll get the same results. But we only need to evaluate 3/2 theta from 0 to 2 pi. Everything else has a period of 2 pi or pi. These are guaranteed to come out the same and cancel each other. This suddenly collapses. R cubed, where'd that come from? How about R squared? 3/2 times 2 pi minus 3/2 times 0. Not sure why I bothered with the 0 as the lower limit since it annihilated the antiderivative. The 2's cancel, that's 0. 3 pi R squared seems to be our area. And it is. The setup of this really wasn't that hard once you had the parametric equations. It was the calculation of the antiderivative and evaluating it at the upper and lower limits and subtracting the results. Again, if that whole ordeal over here about the periods of the antiderivatives compared to the difference between the limits of integration threw you off, don't do it. Substitute the 2 pi everywhere, work it out. Substitute the 0 everywhere, work it out. Subtract your results. Do what you normally do. But the more integrals you do with trig functions and periods and stuff, the more you're looking for shortcuts. And in Calculus 3, trust me, that saves you a lot of time.